I'm Bryan Chalarca. I'm going to present the implementation of viscous dampers as a seismic protection system and its effects on the structural and non-structural seismic response. The outline of this presentation is going to be the introduction of the objectives, then fluid viscous dampers as a seismic protection system, parametric study, the definition, then the result, then prediction model of the seismic response system equipped with fluid viscous dampers. Finally, we move to exploring new engineering demand parameters for non-structural elements, and then conclusion and innovative aspect and future work. So as part of the introduction, we have that earthquakes still represent a significant hazard to modern society. More than 50% of the casualties and 20% of the total economic loss caused by natural disasters were caused by earthquakes. So it is necessary to reduce the seismic vulnerability of buildings by increasing the structural and non-structural seismic performance. But how we can do that? Through the implementation of seismic protection systems. However, those systems can modify the dynamic properties of the structure, and then we need to identify what is going to be the new seismic demand in either the structural part and the non-structural part. So based on this, we have as a main objective to understand the effects of the different parameters involved in the design of fluid viscous dampers and the interaction among them in the structural and non-structural seismic response. To do this, we need the implementation of fluid viscous dampers as a seismic protection system, characterizing what is the important parameters and what are the boundaries of those parameters for our physical implementation. Based on that, we have the structural and non-structural seismic response. With those results, we have the development of prediction models. And then, due to some things that we realized, we need to explore new engineering demand parameters for non-structural elements, especially for the acceleration sensitive ones. So fluid viscous dampers is a device that dissipates energy to an almost pure viscous damping. They are velocity activated. And one of the ideas like there is a fluid in these two chambers, and with the movement of the piston, this fluid is moved, start dissipating heat, and the properties of the device are generated by the characteristic of the fluid and the characteristic of the refining in the piston. So as I just mentioned, there is a force-velocity relationship. There are several numerical models to model the fluid viscous dampers, and also there are several design procedures. So the velocity exponent, also known as alpha, is the one that rules the velocity, the force-velocity relationship and the hysteresis loop of fluid viscous dampers. Here we can see the basic model of fluid viscous damper, in which we have the force is equal to the famous C constant, the damping constant, times the velocity to the power of alpha. So if alpha is larger than 1, we have a lockup device. This is not for energy dissipation, so it's not our concern right now. If alpha is equal to 1, we have a linear viscous damper in which the force is linearly proportional to the velocity. And if alpha is smaller than 1, then we have a nonlinear viscous damper in which we have higher forces and low velocities, and then we limited the maximum force in case of a spike in the velocity. Additionally to that, we have in the hysteresis loop that for a linear viscous damper, we have like a more elliptical shape, having the maximum force at the zero displacement and zero force at the maximum displacement. In the case of nonlinear viscous dampers, we start getting a more rectangular shape, so we are getting closer to the shape of a hysteretic damper, having like a large range of displacement in which we can expect larger forces. In terms of the numerical model, two models are the more common for a structural application. This is the pure viscous, or the famous dashboard element. And then we have also the maximum material. So in the case of the pure viscous, the dashboard, we only have this part, we only have the C and the alpha that characterize the damper. But then in the case of the Maxwell, we have a spring and a dashboard in series. The dashboard again represent the dissipation part, and the spring represent the axial stiffness of the damper and the assembly that supports the damper. So we can have the stiffness of the connection, the stiffness of the brace, and the stiffness of the damper itself. The calculation of this stiffness is a problematic issue because first, for example, for the connection, you can have some clearances that will reduce the actual stiffness that can provide. And also the actual stiffness of the damper is frequency dependent and normally is proprietary information from the manufacturers. So it's not available at a design level to implement these values. Finally, two design approaches were used to distribute the damping constants along the building height. So how to calculate the C? We have first the equivalent lateral stiffness, in which we have a damping constant that is distributed based on the lateral floor stiffness of the building. And this allows us to have a damping matrix that is approximately proportional to the stiffness matrix. And then we have a uniform distribution that calculates a unique damping constant for all the dampers in the building for a given direction. And this is preferred at a low-rising building because it can reduce the testing costs required for some building codes. So now moving to the parametric studies, we have the definition. So two parametric studies were carried out using single degree of freedom system and multi-degree of freedom system. The idea with the single was, okay, we need something simple that we understand what's happening. So we go with this. We have 4 linear single degree of freedom system with periods from 0.5 seconds to 2 seconds. Here we have the model. So we have the inherent damping, the stiffness of the model, and then we have our fluid viscous dampers. In this case, the stiffness of the model was kept constant, and the mass was modified accordingly to get the different periods. Knowing this, we move to the multi-degree of freedom. So we have 3 archetype buildings of 3, 6, and 9 stories. These buildings are part of the Sac Steel project in California that was born after the 1994 Northeast earthquake, with the idea of understanding the brittle behavior of the welding beam column joints typical of that time. And the fundamental period of those buildings are 0.79, 1.48, and 1.89 for the 3, 6, and 9 story respectively. Now, for the seismic input, we use the FEMA P695 far-field ground motion set. This ground motion set is composed of 22 pairs of records, so 44 in total, representative of the Western US seismic hazard, but they were taken for all the world. Since they are far-field, they were recorded at least 10 kilometers far away of the source. They were assumed in Los Angeles, so they were represented by a design spectrum with an spectral acceleration of 0.6 G at 1 second, and the maximum considered earthquake is more or less equivalent to 0.9 G at 1 second. For the single degree of freedom system, we use 4 intensities, and for the multi 10 intensities. The intensities were characterized for the median spectrum, and again, based on the value at 1 second. Finally, the parameters that we use for the calculation of the fluid viscous dampers were, we use 2 numerical models in the case of the single degree of freedom system. So we use the pure viscous, the dashboard system, and the maximum material. However, we noticed that for nonlinear viscous dampers, the dashboard material doesn't show very good results. There were a lot of numerical instability, there were a lot of noise in the result. So at the end, we only keep with the linear dampers, and then for the Maxwell, we have linear and nonlinear. In the case of the multi, we have then only the Maxwell based on the conclusion we got from the dashboard from the single. For damping constant distribution, for the dot, we don't have any, it's a single damper. And for the multi, we have 2 methods, as I explained, equivalent lateral stiffness and the uniform distribution. In terms of the Maxwell stiffness values, 8 values from 0.25 to 5 times the model stiffness. So in order to have a uniform base to compare the results, we decide to give the dampers, the stiffness of the dampers based on the model stiffness. In the case of the multi, 5 values from 0.5 to 4, the times the lateral floor stiffness. In this case, they were based in each floor in the lateral floor stiffness of each floor of the building. For velocity exponent, we have 6 values for both. For the SDOF, we have from 1 to 0.1, so we have linear and nonlinear. And from the multi, again, 6 values, in this case, from 1 to 0.2. For supplemental damping ratios, we have 3 values for both parametric studies, 10, 20, and 35%. So in total, we have 592 SDOF configuration, that's roughly more than 100,000 analyses. And for the multi, we have 543 configurations with more than 230,000 analyses. So the seismic response of these parametric studies was measured in terms in the case of the single, peak relative displacement, peak relative velocity, peak damper forces, peak absolute acceleration, and mass absolute acceleration response spectrum. And in the case of the multi, we have the collapse fragility function, peak individual foundation reactions, peak interstory lifts, peak damper forces, peak floor acceleration, floor absolute acceleration response spectrum, and spectral annual losses. So now with the results, let's start with some results from the single degree of freedom parametric study. So the displacement response is as expected. We have reducing values of the relative displacement with increasing values of the maximum material stiffness. It's important to highlight in these graphs that they are normalized values with respect to the control building, so it's easy to identify what is going to be the trend of the different configuration of the viscous dampers. That's why here we have the line at 1. So as I was mentioning, we have that for low intensities, we can notice that it's coming, okay. We have noticed that we have a variation based on the velocity exponent and the maximum material stiffness. So in the case, we have nonlinear viscous damper with very low values of the alpha coefficient. We can see that we can have, sorry, okay. We can have a reduction in the relative displacement. In the linear case, it's not that much influenced by the maximal stiffness, but still we have a better implementation with high values of the maximal stiffness. For high intensities, the influence of the velocity exponent is not that big. However, we still have some difference between the low values and high values of the maximum material stiffness. In the case of the acceleration, we notice that the response is highly influenced by the implementation of the viscous dampers. We can see again that for, okay, it's coming. So with increasing values of the maximum material stiffness, we tend to have lower values of the peak acceleration, as you can see here, the difference in the color. But then also by implementing nonlinear fluid viscous dampers, we have an increment in the peak acceleration as the velocity exponent is reduced. So as we can see here, so as you can see here, there is a reduction. The linear cases show a smaller peak acceleration, and then the nonlinear cases tend to show a higher peak acceleration. Even there are some cases, as you can see, we have values larger than 1, which means that we can have peak acceleration larger than the control system. In the case of the high intensity level, we have a several trend, but again, it has less influence by the maximum material stiffness. But then we decided to occasionally check what is going to be the actual seismic demand, acceleration demand on non-structural elements. So we calculate the response spectrum based on the acceleration time histories of the mass of the single degree of freedom. And from here, there are several things. One, we can see that we are expecting the peak spectral acceleration to happen in at the same period of the system. So this is the blue line here at 1 second. That is the equivalent of the M2 system that I'm showing here. But then with the maximum stiffness and the velocity exponent, we realize that there are several behaviors that are happening here. First, there is a stiffening effect that you can observe, but as we increase the maximum stiffness, the peak of the spectral acceleration is not happening at the period of the system, but it's happening to a shorter period. So we are kind of stiffening the system. And also with the velocity exponent, we are having like a kind of an amplification of the demand. So in some cases, for example, here, with very low values of the maximum stiffness combined with low values of the velocity exponent, we can have a peak spectral acceleration larger than even the one of the control system. So again, we can increase, we are modifying the dynamic properties of our system. So the discussion for this part is, in general, fluid viscous damper, we use the peak response values. High maximum material stiffness values assure an efficient implementation of fluid viscous dampers. And nonlinear fluid viscous dampers show a stiffening effect accentuated by the maximum material stiffness, the level of supplemental damping, and the velocity exponent. Now moving to the multi, we have first the collapse fragility function. So the sideways collapse was explicitly modeled in our buildings, considering the flexural and external degradation in the plastic hinges, and the collapse was calculated as the numerical instability due to large displacement. So based on the 10 intensities, we calculate the probability of collapse. With the maximum likelihood estimation, we obtain some fragility functions, and those functions were corrected using the FEMA P695 methodology to obtain the correct fragility function. And based on this, we calculate the probability of collapse, in this case for the maximum considered electric intensity. If you let me zoom in, we can see that there are different trends that we can identify here. First, larger values of the supplemental damping produce a smaller probability of collapse, as expected, but also increasing values of the maximum material stiffness tend to show a smaller probability of collapse values, and decreasing values of the velocity exponent also tend to show higher probability of collapse. Now moving to intersoil rifts, we have an expected behavior that supports the current practice of the preferring small velocity values. So right now, practitioners say that the smaller the alpha value, the better. So here again, we are talking about normalized values. Again, we have everything normalized with respect to the control system. So that's why we have these lines here at 1. And zooming in one of the examples, we can detect several trends. Again, increasing values of the maximum material stiffness permit a better implementation for the viscous damper, having a smaller peak into soil rift. The increment of the supplemental damping can have a variation based on the velocity exponent. So combination of high supplemental damping and low values of the velocity exponent tend to show, especially with low values of the maximum material stiffness, tend to show larger values of the peak into soil rifts. But then configuration having larger values of the maximum material stiffness. In this case, so we have an efficient implementation of fluid viscous dampers. We can see that the nonlinear viscous dampers tend to have a low peak into soil rift. So this result shows that's why nonlinear viscous dampers are preferred, because we are limiting the displacement, so we are limiting the demand on the structure. However, again, thinking about non-structural elements, the peak floor acceleration show a complete opposite trend. It can be larger than the control structure and are highly influenced by the supplemental damping, the velocity exponent, and again, the maximum material stiffness. So we are looking again at normalized graphs, and checking one of the examples, we can see again, increasing values of the maximum material stiffness show lower peak floor acceleration values. Increasing values of the damping show increasing values of the peak floor acceleration. So putting more damping is not beneficial in this case, at least for non-structural elements. And also the velocity exponent, as we can see here, is going to be that non-linear viscous dampers tend to show smaller peak floor acceleration compared to non-linear cases in which we can have very large peak floor acceleration. Even some configuration, as you can see here, tend to have acceleration that are several times larger than the original building. So based on this, again, we decide let's calculate the floor spectral acceleration and what is happening from the dynamic response in buildings equipped with fluid viscous damper. So we can notice here, again, increasing values of the maximum material stiffness tend to show the smaller floor spectral acceleration, but increasing values of the supplemental damping are showing larger values of the floor spectral acceleration. So again, putting more damping can be detrimental for non-structural elements. And from the point of view of the velocity exponent, we can see that the linear case that is represented by the black line show a smaller floor spectral acceleration, and then the extreme case of the nonlinear viscous dampers can show peaks that are very large, even several times compared to the original structure without dampers. Additionally to this, and remembering the stiffening effect we observed in the single, here we can see something similar. So we are expecting that the peaks, as I said, happen to the periods of the building. In this case, I'm showing here 3 periods, the 3 first periods of the building, or even to larger periods due to the elongation of the periods, due to the yielding of in high intensities. However, as you can observe here, with increasing values of the maximum material stiffness, you start getting that the peaks are happening more to the left, to shorter periods. So you can observe here, we have a not very efficient implementation, so 0.5 times the floor stiffness, and you start getting a shift to shorter periods. And as we move down, sorry, the animation are not working very quick, but they are coming. Okay, too much. So as you can observe, the peak spectral acceleration, at least here, the one related to the fundamental period of the building, is happening to shorter non-structural periods compared to the control building. So we decide we need to understand what was happening here, from where is coming this stiffening effect, because it's supposed that or at least that is what is thinking in the practitioner world, that fluid viscous damper doesn't modify the dynamic properties of the building, at least not from the stiffness point of view. So we decided, okay, from the maximum material, we have a spring part. So we implemented that spring part as a brace of the system with the same value of the stiffness. We calculate the periods of these brace structures. We calculate brace periods, and we realize that these periods corresponds to the shortening we are observing here. So in fact, the implementation of fluid viscous dampers are changing and modifying the stiffness of the structure, at least from the dynamical point of view, and we can see this in the results of the fluid spectral acceleration. Finally, to compare, okay, but what is a good implementation? Because we had one trend going on with the rift, one trend going on with the acceleration. So we need something to calculate the overall performance of the building. So we calculated the specular and losses following the FEMA P58. So the buildings were equipped with typical non-structural elements of an office use. And based on that, again, we have several results. First, we can see that, again, we are looking at normalized values with respect to the control building. That's why everything here is at 1. Another thing that is important is that some configuration of fluid viscous dampers can show a specular loss larger than the one of the control building. So again, implementing fluid viscous damping, we are expecting a better performance, but can be detrimental due to this combination of acceleration and rift. Additionally to that, again, we have that the increasing values of the maximum material stiffness should tend to show a smaller specular losses, and reducing values of the velocity exponent also tend to show increasing values of the normal specular losses. Additionally to this, there is another point that is important to notice, and is that big values of the supplemental damping doesn't mean better performance. For example, here we can see that the very high value of the supplemental damping, 35%, are causing larger specular losses compared to other ones. So in this case, for an efficient implementation, we can say that a middle value, kind of 20%, is a good option, because we are kind of controlling the rift, but also limiting the amplification of the acceleration demand. So the discussion for this part is that the acceleration response is highly sensitive to the variation of fluid viscous dampers. There is no clear winner between linear and nonlinear viscous dampers. More damping does not necessarily mean better performance, and the trade-off between displacement and acceleration dominates the overall seismic performance of a building. But then, with this huge database that we create with all the different parameters, we decided to create some prediction models that can be useful at design stages. So we implemented a Gaussian process regression that is a very robust methodology that can take into account all these different parameters to predict the seismic response of the structural system equipped with fluid viscous dampers. The prediction models are based on normalized seismic values, so to reduce like the influence of the inelastic behavior of the structure, at least a little. And based on that, 10 prediction models were generated. 4 for the single degree of freedom, being the peak acceleration, peak spectral acceleration, peak relative velocity, and peak relative displacement. And for the multi, we have 6, 3 for the ELS distribution of dampers, and 2 and 3 for the UD, based on peak interstory rift, peak floor acceleration, and peak spectral acceleration. And as you can see here in those graphs, we have a good matching between the actual values and the predicted values. They are very close to the perfect prediction of the line. So example building was used. So a four-story building was equipped with fluid viscous damper with different properties of those used in the parametric study to check what's going to be the prediction, what's going to be the matching with our models. And here, for example, we have for the peak floor spectral acceleration, and we can see that we have a very good approximation, especially at low intensity. So we are not expecting a lot of yielding in the structure. So we have a good matching. However, even in higher intensities, we have a good approximation. So as a discussion, we have that the flexibility of the GPR models allowed further optimization of the prediction model. So we can modify that, increase the number of data, the number of training points to improve the models. And the prediction model are useful and at early design stages to consider the impact of the variation of the design parameters for viscous dampers. We are not intending to replace nonlinear time history analysis, but at least to provide a tool that, okay, I want an alpha opt-in for this alpha. So what's going to be the demand either in the structural part and in the non-structural part? Finally, exploring new engineering demand parameters for non-structural elements. So EDPs are a critical parameter to carry out seismic performance assessment because they characterize the demand and the limited states of the element that we are looking for. Peak floor acceleration is current the EDP for acceleration sensitive non-structural elements, and the flexibility of the non-structural element is usually considered to the implementation of a fixed amplification factor. So we did a comparison with our results with the different configuration of fluid viscous dampers. What is going to be the peak amplification factor? So is the division by the peak floor spectral acceleration divided by the peak absolute acceleration. And first thing we realize, we are very far away of the fixed 2.5 value. Additionally, again, the implementation of fluid viscous dampers modify this response. And in some cases, we can have a peak amplification factor that is even larger than the control building. So again, we need a new EDP that is able to represent better the demand, the acceleration demand on non-structural elements, even in building equipped with fluid viscous dampers. So based on this, we explored several possible EDPs. So acceleration-based EDPs, in this case, we check two possibilities. So one is the peak floor acceleration amplification factor. So try to calculate this amplification factor. The other one is the floor absolute acceleration response spectrum. We evaluate several methodologies, just some publicity to Roberto. Additionally to this, displacement-based EDPs, so floor relative displacement response spectrum. We did some comparison, and we are, as you can see here, we are getting good results between the target displacement and the median displacement from nonlinear time history analysis. And finally, some energy-based EDPs. In this case, we use plastic energy based on the floor relative velocity response spectrum and cumulative hysteretic energy. So in this case, we have an example of performance-based plastic design, which use the floor relative velocity response spectrum. And again, as you can see here in the table, we have a good matching of the target design displacement and the median peak displacement time from nonlinear time history analysis. So as a discussion, we have the current EDP for acceleration sensitive non-structural elements can lead to inaccurate and conservative assessment. There are new methodologies that simplify the calculation of the seismic demand and allowing a more exhaustive assessment. So as conclusion, we have that the calculation of the maximum material stiffness can be problematic and can lead to conservative design or inaccurate performance assessment. A maximum material stiffness of at least twice the system stiffness or lateral floor stiffness is recommended to allow an efficient implementation of fluid viscous dampers. The stiffening effect that is represented by the brace period and the amplification of the acceleration demand is governed by the level of supplemental damping, the velocity exponent, and the maximum material stiffness. Nonlinear fluid viscous dampers do not necessarily exhibit a better seismic performance compared to linear fluid viscous dampers. The acceleration response is highly influenced by the design parameter of fluid viscous dampers, and the current engineering demand parameters for acceleration sensitive non-structural elements do not represent well the actual acceleration demand, especially in buildings equipped with fluid viscous dampers. So innovative aspect and future work, we have identification of the influence of the diverse design parameters of fluid viscous dampers on the seismic response of a structural system, especially in regarding the acceleration demand on non-structural elements. Development of a prediction model of seismic response of a structural system equipped with fluid viscous dampers. Exploration of a new engineering demand parameters for acceleration sensitive non-structural elements. And the development of simplified methodology to apply performance-based plastic design to the acceleration sensitive non-structural elements. As future work, we have the characterization of the actual elastic stiffness of fluid viscous dampers, how we see it can be problematic and influence a lot the results. Identification of the influence of the design parameter of fluid viscous dampers under near field ground motion, or including damper failure mechanism, and development of new engineering demand parameters for acceleration sensitive non-structural elements. This is a list of publications we created during the development of this thesis. Thank you very much.